Welcome everyone. Today our problem is lead code number 1266, minimum time visiting all points. So, let's see what the question states. The question states, on a 2D plane, this is the 2D plane, example of a 2D plane, there are n points with integer coordinates, points of I equal to xi comma yi. That means we will be given the coordinates like this, 1 comma 1, 2 comma 2. Here you can see the example of the coordinates given in an array format where each points of I, this is the points array, each points of I will contain a coordinate. That means 2 points, the combination of 2 points. That's called a coordinate. Now, we need to return the minimum time in seconds to visit all the points in the order given by the points array. Now, the points array is given 1, comma 1, 3, comma 4, minus 1, comma 0. Let's see in the example. This is the point 1, comma 1. This is the point 1, 3, comma 4. This is the point minus 1, comma 0. We need to visit these 3 points by this order only. You can't say that I will first visit 1, comma 1, then I will visit minus 1, comma 0, then I will visit 3, comma 4. You can't do that. You need to go step by step. You need to continue this flow. First, you need to visit 1, comma 1, then 3, comma 4, then minus 1, comma 0. Now, you can move according to these rules. Let's see what these rules are. In 1 second, you can either move vertically by 1 unit. In 1 second, you can either move vertically by 1 unit. That means this is the movement you can do, or this is the movement you can do, up or down. This is the vertical movement you can do. You can do by affecting 1 second from your total time. And you can move horizontally. That means this direction. Vertical or horizontal costs 1 second each. Move diagonally square root of 2 units. In other words, move 1 unit vertically, then 1 unit horizontally. That means this move. Like from here, you are going to there. This move, you need to first go horizontally, then vertically. So this contains a complete diagonal move, and a diagonal move also cost 1 second. So look at this. Like, are you getting an idea that the diagonal move is so important that it, as we are asked minimum time in seconds, then are you getting an idea that we need to maximize the use of the diagonal move so that we can get a global minimum time? Let's see. Let's see. We will see the entire observation. We will see, and just some more for some more clearer observation, there are some sort of points you need to consider. This, you have to visit the points in the same order as they appear in the array. Just what I have told you, that you need to maintain the order. You can't break the order. You need to first go 1 comma 1, then 3 comma 4, then minus 1 comma 0. And you are allowed to pass through points that appear later in the order, but these do not count as visits. It's one of the most important points here. You need to consider this, because suppose you visit first 1 comma 1, you are starting from there, so you will obviously visit it. Then in the way of going to 3 comma 4, whichever you find the shortest way, in the way of going to 3 comma 4, you encountered this coordinate minus 1 comma 0. Then you can go from there, you can go through there, but it won't be count as visited. You first need to go 3 comma 4 through minus 1 comma 0, then you have to again go 3 comma 1 minus 1 comma 0 from 3 comma 4. So it won't be counted as visited. That's the thing it's stated here. So all the points are clear. Now let's see some observations. For this example, first let's through this example, points 1 comma 1, 3 comma 4, minus 1 comma 0. The points we need to visit, I have just marked them green, so you don't have to, like, you don't to have to worry. So point 1 comma 1 is there. So if we want to go point to 3 comma 4, then let's see how many diagonal moves we can do. Point 1 comma 1 to point 2 comma 2, point 3 comma 3, Now, we can't go more diagonal here. We need to go vertical. So, vertical going, we are going to the point 3 comma 4. Then, let's again go diagonal. 2 comma 3, 1 comma 2, 0 comma 1, minus 1 comma 0. So, we encounter the point minus 1 comma 0 here. What is the total path? This cost 1, 1, 1, 1, 1, 1, 1. Total, we are getting 7. So the output is 7. The minimum time in seconds to visit all the points in this array, in this order, is 7 seconds. So the total time will be 7 and the output will be 7. Now we will see how we got this idea. Can you see some observations? Like, we need to maximize the use of diagonal paths because it's the most rewarding path, right? It's not just more rewarding, it's the most rewarding path, right? Because the it takes the minimum time and gives us the maximum distance to be covered. So we are getting an idea, right? Because if you want to go from this point to this point, the most most efficient path is the diagonal path, right? If you go to in the horizontal then vertical path, it will cost 1 plus 1 2 seconds. It will cost 1 plus 1 2 seconds. But in the diagonal path, it also costs 1 second, and you can go from here to there. So the diagonal path is the most efficient path. We need to maximize the use of it. How? Now, what are the cases we need to consider for a movement? Example. Example. Suppose we are given the coordinates 2, comma 2, 3, comma 3. It requires one diagonal movement. You can picture it here, right? This is 2, comma 2. This is 3, comma 3. So we need one diagonal movement. That means 1 second. Then take the coordinates 1, comma 2, comma 3, comma 4. For this case, now, first what we will do is try to use as much diagonal movement as possible to get closer to the final coordinate. Like we are starting from this coordinate 1, comma 2, and we will use as much as diagonal moves as possible to get closer to this point, and then we will go the remaining moves in horizontal or vertical, whatever is needed. So the observation is for diagonal movement, both points of the coordinate gets affected by, let's see how it works. From point 1, comma 2, it moves diagonally, it goes to point 2, comma 3. One, the x is here, the x comma y, both is increased by 1. So 1 is increased by 1, 2, and 2 is increased by 1, 3. So 1, comma 2 goes to 2, comma 3. This is how a diagonal movement works. It goes x comma y to x plus 1 comma y plus 1. Then it again moves diagonally. Then it goes again x plus 2 plus y comma y plus 2. 2 comma 3 to 3 comma 4. You get an idea that how the diagonal movement is working. Now, here it covers the whole distance in the diagonal path so that the total time is equal to 2. Two diagonal movements. Let's see a mixed scenario. Here we needed to go from 1 comma 2 to 3 comma 4. So we achieved that only from the diagonal movements. So we don't need to go vertical or horizontal or a straight path. We achieved it only by diagonal moving, by moving diagonally only. So let's see a mixed scenario where we need a diagonal plus straight path. Now let's see a mixed scenario. The coordinates are 1 comma 1, 3 comma 4. Now first, as we need to maximize the diagonal movement, we need to first move diagonally and match one point, either x or y, whichever is minimum, right? Either x or y, whichever is minimum, keep it in mind. We will see that in the example. Then move straight to go to the point to get the minimum distance. Now, 1 comma 1, our final goal is 3 comma 4. So from 1 comma 1 we move diagonally, it costs 1, we go to 2 comma 2. Then it again goes diagonally, it goes to 3 comma 3. Now x here, the x, it's in the form of x comma y, right? 3 comma 3 is in the form of x comma y. So the x here is 3. The x 3, which is 3, matches with the destination coordinates 3 comma 4. So uh, yeah, the x3 matches with the destination coordinates 3 comma 4 x. So the destination's coordinate is 3 comma 4, which is x. We need to consider 3. Here is also 3. It matches. The both x matches. Then we need to consider a straight movement. Either horizontal, either diagonal, we need to consider a straight movement so that we can go to 3 comma 3 to 3 comma 4. Because as we achieved the x, which is 3, then we don't need to go diagonal again, right? Because moving diagonal means we need to increase this x and y both. So here, if we have gone diagonal, we would have gone to 4 comma 4, but we need to go to 3 comma 4. Our final destination is 3 comma 4. So we considered a straight movement so that we can only affect one point of the coordinate. So it goes from 3 comma 3 to 3 comma 4. Now, what is the formula? Let's see. The formula we are working on is, so extremely sorry for the pause. The laptop's charge is gone and I just plugged in. So yeah, now let's continue. So we are here for the formula. Point 1 is x1 comma y1. Let's consider point 1 is x1 comma y1, the coordinate, and the coordinate 2 is x2 comma y2. Now we need to find del x and del y. How? The del x will be the absolute value of coordinates 2's x, that means x2, minus x1, coordinates 1's x. And the del y will be the absolute value of the coordinate 2's, that means y2, minus y1. After we get del x and del y, what is our total? Our total is diagonal moves plus the remaining moves. We are maximizing the diagonal moves, right? And after diagonal moves are completed, there will be remained some moves we need to consider for the straight moves. So that comes under the remaining moves. The formula for the diagonal moves are total equal to minimum of del x comma del y plus minimum of del x comma del y, whichever is minimum. We need to go to the diagonal for this, and then the maximum of del x comma del y minus the minimum of del x comma del y. This is the entire distance we need to consider for the straight movement. Now it will be minimized to, if you see here, if you clearly observe here, this will be minimized if we just go out of the bracket. Then this minus minimum of del x comma del y and plus minimum of del x comma del y, both will be cut, and our final will be total equal to maximum of del x comma del y, right? And let's apply this formula in an example to see how exactly it's working. So let's use this example, 1 comma 1 comma 3 comma 4. Okay, we need to go to 1 comma 1 to 3 comma 4. Now let's calculate the del x. The del x will be this x2 minus x1, that means 3 minus 1 equal to 2. Del y will be 4 minus 1 equal to 3. The total is maximum of del x comma del y, which I have derived the formula, right? The maximum of del x comma del y. So what is the maximum of del x comma del y? Maximum of del x comma del y 2 comma 3 is 3. And so we need here two diagonal movements plus one straight movement. Now, what is the algorithm? The algorithm is now very simple if you see it clearly, that we need to initialize the total time equal to 0, and we need to loop from 0 to n minus 2. Why not n minus 1? We will see. for each coordinate points I and points I plus 1. This is the reason we need to loop up till n minus 2, because we are considering the points of I, this index and the next index. If we would have gone to n minus 1, then it would have been out of bounds. We couldn't find that I plus 1 for the last index. So then calculate the dx and dy. We just have calculated this like this, and the total time plus equals to the maximum of dx comma dy. So the local maximum is just added up to the total time, which is the global minimum, and we return the total time. So it's an greedy approach. Let's see if we can code it up or not. Uh, let's initializing total time equal to 0. We have just discussed that we will go up till n minus 2. So as it lesser than, then up till n minus 1. Where is my cursor? Okay. So calculate the dx. The dx is the first point, the x, and it's the x2 minus x1, and we would take the absolute value. And let's calculate the dy also. What is the dy? The dy is the y2 minus y1. Now, what we are now doing is we have calculated the dx and dy, and we will now add up the total time. Add up the maximum of dx comma dy to the total time, because that's how many seconds we need for this point to this point. The time plus equal to maximum of dx comma dy. At the end, we will return total time. Let's see if it works. Uh, Sorry for this minor error. It should compile now. Yeah, it compiles. Let's submit it. We should get a AC. Yeah, we got it. The best time complexity we could have got. The best space complexity we could have got. Very simple problem. An easy level, but if you are not familiar with the coordinates, then it can be a little hard to digest, but at the end it's pretty digestible. So yeah. So good night and farewell.